Welcome, everyone, to today's podcast. I'm your host, Joanna, and I'm thrilled to have with me today, Sally, Matthew, and Kimberly to discuss some groundbreaking research in chemical engineering.
Hi everyone. Excited to be here.
Great to be here, Joanna.
Likewise. This research sounds fascinating.
It is. Today, we'll delve into a fascinating paper by Maya Bhatt and John Kitchen on finding classification boundaries in engineering applications. It's all about improving efficiency and accuracy in identifying boundaries between different outcomes, a task crucial in many engineering fields.
Sounds complex. What kind of boundaries are we talking about?
Exactly, Sally. Imagine you're controlling the temperature of a shower. You want a specific range of temperatures, but the hot and cold water flow rates are your inputs. The boundary is the line separating the right combination of flow rates that produces the desired temperature range from the combinations that don't.
That's a very clear example. So, how do they approach this problem?
That's the really interesting part. The traditional way is using a grid, testing every point. Very inefficient and time-consuming. The authors introduced three clever sequential sampling methods to improve this: broad initial sampling, low point density, and path tracing.
Okay, let's tackle broad initial sampling first. What's that all about?
It's like casting a wide net initially. You take a few initial samples scattered across the entire possible parameter space, kind of randomly, then you see where they fall into your class's desired outcome or not. Then based on where those points are, you refine the areas that you sample next.
Exactly, Matthew. Think of it like searching for gold. You start by panning in several different spots. If you find gold in one spot, you concentrate your efforts there.
So, it's smart because you are not wasting time in areas which aren't promising?
Precisely. It's about efficient exploration. The next method, low point density, is a bit more focused.
Focused how?
Well, instead of starting completely randomly, you have some idea of where the boundary might be, then you sample densely around that area and expand outwards, focusing on the regions that are most uncertain in their classification.
That's right. It's like you already have a rough map, and you're refining it by concentrating your samples near the edges of what you've already found. So you have more samples around the boundary, where you aren't certain.
The third approach, path tracing, is really clever. It's like drawing a line along the boundary.
How does that work?
You start near the boundary and follow its contours. At each point, you take a small step along the boundary and test the classifications. If you're still within the boundary, you keep going. If you've gone outside, you go back. It's like drawing a line, always staying close to the edge.
All three methods are powerful, but each has its strengths and weaknesses. This is great for initial exploration, LPD for refining an existing estimate, and path tracing for accurately following contours.
The paper shows how these methods work in three different scenarios: the shower example, finding an oxidation boundary in a metal alloy, and finding a phase boundary using a complex equation.
Amazing. What were the results?
All three sequential sampling methods drastically outperform the traditional grid-based approach, needing many fewer experiments to achieve similar or better results. They were able to improve accuracy and even quantify the uncertainty in the boundary location.
The study showed that the best method depends on the specific situation. If you need high certainty and a clear boundary, path tracing was the winner. However, broad initial sampling was quicker when there was a large range of possibilities to explore.
And this research opens up some really exciting possibilities. These methods can be extended to more complex scenarios and even used to find multiple boundaries at once.
This is truly amazing work. Thanks for explaining it so clearly, all of you.
My pleasure. I was equally fascinated by the results and the way they addressed such an important engineering problem.
Absolutely. And that's it for today's episode. Thank you for listening to this insightful discussion on efficient boundary identification. Join us next time as we delve into another fascinating topic.